cards. Okay, moving right along. So today we'll talk about steel and other metals and their uses in architecture and construction. This is the second of 4 lectures that I'll be giving you. Really what we're talking about mostly is going to be steel, because in the first part of the lecture, because it's the primary metal that's used structurally in architecture and construction. Okay, other metals have been used structurally, but aren't as much anymore, and I'll go into that when we get to them. Steel comes from iron. Iron has a density of 7,874 kilograms per meter cube. Is it going to float or sink in water? Sink. And why is that? Because water's 1,000, not 1,100. Water's 1,000 kilograms per meter cube, so anything bigger than that is going to sink, right? Now, quite amazingly, pure iron has only got a strength of about 10 megapascals. All right, so that's like a kind of that's a timber type strength, even though it is iron, and that's because in its pure form it's quite soft. And it's only strengthened by smelting, alloying, and working. So smelting basically means melting it down and doing something else with it. Alloying means that you mix it with other metals, or other things, and the combination of the two actually makes it stronger. And it's mixed in its molten form, right? So it's mixed while it's molten. And working means things like hammering it into shape, or pressing it into shape, and so on and so forth. Basically, applying mechanical processes to the iron in order to make it stronger. All right. Now, steel is made from iron, but the definition of steel is that it is iron that is smelted with certain amounts of carbon. So steel is actually an iron alloy. All right, that's the base thing. It's going to get a little complicated because steel itself can then be alloyed with other things to become stronger as well. So steel, as you can see, has much the same density. It will still sink in water. But you can see that its strength for mild steel, which is an average sort of structural steel nowadays, has a strength of about 480 megapascals in tension. So that's 48 times stronger than pure iron. As a metal, it's not got a lot of moisture in it like timber can. And its characteristics are that it's plastic when it's molten, which means it can be made into different shapes while it's in a soft liquid form. It is ductile when it solidifies, which means that its shape can be changed by bending, folding, and so on and so forth, without breaking the thing itself. And it is, in terms of its structural characteristics, it's good in both tension and compression, like timber. So there are 3 main forms of steel, 3 varieties of steel, if you like, that are mostly used today, although they are certainly not limited to this. Mild steel is the most basic form, which is used in construction, followed by stainless steel, which is steel that has been alloyed with chromium and nickel. Now, stainless steel is stronger than mild steel, but it also has the characteristic that it's resistant to rusting. Rusting is oxidation, is one of the ways that steel degrades. And the third kind of steel is called chrome molybdenum steel, which is a steel that has been alloyed with chrome and molybdenum, which then makes it very strong. Okay, mostly used in tubular form. And then there's a whole stack of other alloys that are put into steel, which allow the steel to have various characteristics. Some good, making them much stronger, so you can make them much thinner also. Some bad, because while they might be stronger, they also become more brittle. Some of them need to be heat treated, some of them are affected by heat, and so on and so forth. So this is more just to tell you that this is out there, and that there are many different processes that steel can be put through to get different kinds of characteristics. Now, in physical form, steel can be found in terms of wire, cable, rod, and mesh. So rods are kind of sticks, and mesh is basically a grid of rods welded together. Steel plate, tubes, hot rolled sections, and cold form sections. So we'll go through hot rolled and cold form in a little bit, but you can see that steel is a material that can be made, drawn, formed, extruded into various, not actually extruded, sorry, that's the wrong word, made into various different shapes and forms and lengths and so on. And that's got to do with its ductility. It can be made into quite a thin wire while still maintaining quite a bit of strength. So, if we go back to look at the history of iron and steel, really the Iron Age is completely ancient, right? We're talking about millennia before the Common Era. Now, the Common Era is used to be known as the before Common Era used to be known as before Christ or BC. Now we use the term before Common Era, BCE. Okay. So interestingly, steel wasn't actually used that much for a long time, or at least the development of steel did not go through big leaps and bounds for a long time until the 19th century when they started to learn how to make stronger forms of steel, which were also mass producible. So cast iron is probably the most basic form of turning iron ore into something. It has some carbon mixed into it to bring the melting point down. And what happens is that you basically pour it into a mold of something useful, such as a frying pan, as you can see on the right. But it is quite brittle, so it's got a strength of only 27 to 55 megapascals, which is a bit stronger than the strongest timbers. Now, cast iron also allowed elements of the same shape to be mass-produced, to be, you could pump out thousands of them. And this was the technology that was used to build the Crystal Palace in 1951, which was built for a big international exhibition in London by the landscape gardener Joseph Paxton. So what happened here is that a series of standard elements were cast into these molds and then bolted together to form this building together with glass. Now, so that's what cast iron is. Wrought iron is smelted iron that has been worked by forging, extruding, rolling, hammering, and so on, which makes it significantly stronger. So you can see cast iron was only up to 55 megapascals, but the moment you start to forge it, which is basically to press it into a form under pressure rather than just pour it into a jelly mold, extruding it and rolling it, hammering it, and basically working it, it becomes much stronger. So the best example of a wrought iron building is the Eiffel Tower not in London. Let me just fix that. This is a problem with copy and paste, right? In Paris of 1889 by Gustave Eiffel, another structure that was built as a gateway building for an international exhibition in Paris. So essentially, it needed a lot more work, but you needed a lot less members to be able to get something of the same strength. Now, this was 1889, and in 1850, you already had the wrought iron technology in France, and this building, the Bibliothèque Saint-Geneviève in Paris by Henri Labrouste, is a building that uses both cast iron elements, as you can see with these columns here, with the cast as well as the cast sort of column heads and the cast bases, as well as wrought elements which are then assembled together. And in the stacks here, you can see that much better examples of all the different wrought iron elements that were used in it, and used with, together with glass for glass roofs and what have you. So we're beginning to see that it's being used for everyday buildings. Steel, of course, when it was first being used, it was only deemed to be a temporary material. The Eiffel Tower and the Crystal Palace were both temporary buildings. Crystal Palace was taken down very soon after, and the only evidence of the Crystal Palace we have left is the Crystal Palace English Soccer Club. Whereas the Eiffel Tower has managed to survive until today. Now, in the 1850s, there was a process called the Bessemer process that was invented in order to be able to produce steel. So steel, of course, is stronger than wrought iron as well. And that involved blowing air through molten iron, which had the effect of removing impurities. So this allowed for the next level of strength in terms of products made from iron. And this was really this kind of steel was the one that actually fed the whole skyscraper boom in New York and in Chicago in the late 19th century. So if you just look at these pictures, in particular this one here, and look at the number of members you've got there, and compare it to, say, to this, you've got a lot less members than you did in the Crystal Palace, right? So what that means basically is that you can, because you're using less of it, each one is actually stronger. Or actually, because each member is stronger, you can use less of those members to make things like buildings. Now, that's the history of it. I mean, the way that you procure iron ore, iron comes from iron ore, is that you dig it out of the ground. Okay, and this has been done for millennia. But what's happened in the late 20th and early 21st century is this is done on a vast and industrial scale. So you can see the size of the hole there. I mean, this truck that you see here is about the size of half of this room. Okay, so you can tell the levels to which we as humans will go to actually get this stuff out of the ground. And of course, one of the reasons for this is that iron ore is one of the, there's a lot of it on the crust of the earth, okay? So it's easily available and it's easy to get out, even though it leaves huge holes in the crust of the earth. So once it comes out of the earth, it's then shipped to iron mills or steel mills where the iron ore is then smelted into liquid form, which is the first process in getting it into shapes where it can be used. So when it's smelted, it's then basically rolled into various blanks. Blanks are just a term which means it's a piece of iron that's then going to be used to be made into something else, okay? And blanks, of course, come in all shapes and sizes depending on what you want to make it into. Interestingly, blanks can be big planks, such as this, but can also be coiled rolled up into big coils like this. So the first kind of steel sections that we'll talk about is hot-rolled sections. So essentially, hot-rolled sections are made from the various blanks that are produced. And to get them into this shape, you basically need to heat up your blanks to a certain temperature where it starts to soften but not fall apart, okay? So, and let me, before we get onto that, these are just your common sort of sections. So what we have here is rectangular hollow sections, RHSs, rectangular hollow sections. We have circular hollow sections, or CHSs, which are, also called pipes. We also have square hollow sections, which is basically one of these, which is square in section. But in the construction industry, we also have things like channels, steel angles, and steel universal sections, which come in universal beams or universal columns. Universal beams are much deeper in their section than universal columns, which tend to be more square in their section, meaning the height and the width are more similar. Quite often called I-beams as well, incorrectly. So what happens with the hot rolling process is you essentially get a bit of a blank, which is roughly formed into a rough shape, which is then reheated and is put through all these processes, and you end up with something that looks like this. So essentially, you can see through a series of rollers here, this blank here starts to be formed into a universal beam section or universal section. And then through a series of other rollers, then slowly it gets rolled and rolled again and pressed until it turns out to be this shape or this shape. And channels and angles also go through the same process to be formed, all right? So what you've got here is something that is formed under heat and pressure, which then also increases the strength of the steel. Mind you, the shape of the hot rolled sections also make those members quite strong. Now, famous users of these kinds of steel members would be the Crown Hall building at the Illinois Institute of Technology by Ludwig Mies van der Rohe in Chicago, 1956, and the building that he inspired, Skidmore, Owings and Merrill's Lever House in Manhattan, which was the first a large curtain wall building in modern building to be built. Now, please excuse me when I use these names, because it is a habit of architecture, because architecture is such a complicated activity, and there are many different groups of people involved in both architecture and construction and getting a design built. However, architects, because there's so much to talk about, architects tend to abbreviate the creators of buildings down to one person, like Mies van der Rohe, or one firm like Skidmore, Owings and Merrill. So it is not my intention here to say that Mies actually got out there and with a rivet gun and put the whole thing together. It is just a short form to say that he was the guy who designed the building. All right? So for you guys, when you're talking about architecture, please keep this in mind. It takes a lot of people to get to build a piece of architecture, and the habit that architects have, which I also have, to only use the name of the architect is only a short form, because there's so much to talk about. It doesn't mean that that architect did everything. Okay, any questions? Okay, moving right along. More recent steel projects are the Great Court redevelopment in the British Museum by Foster and Associates, where the use of computer drafting and 3D modeling, BIM, and also computer numeric controlled milling of steel elements has allowed for very complex shapes. Another example, perhaps more amazing than Norman Foster's one, is the Phoenix TV headquarters in Beijing of 2012 by BET and UFO. Okay, so steel has become the predominant structural construction material, construction metal used in the world today, purely because it's easily found and it's very low tech in terms of making iron ore into steel. Now, other uses for steel are with steel framed doors and windows. These are favored by architects because they're very slim and very fine in their profile, and generally they're used in the industrial buildings because of their of how they react to heat. They can last a lot longer in a fire than other metals or timber for the same cross-sectional area, right? So architects do like to use these things. I think they're quite beautiful, but they're not very thermally efficient. We won't go into that right now, but that's one of the reasons why they're not used more. Quite common nowadays is cold form sections. Now these window sections here are all hot rolled sections, as well as these tubular sections, or the circular hollow sections and rectangular hollow sections used here. The other form of steel that's very commonly used is called cold forming. And what happens with cold forming is you take a coiled up sheet of very thin steel between 0.2 and 0.7 of a millimeter, maybe 1 millimeter in some cases, and you fold it into the shape that you want, or roll it into the shape that you want. So you see with these kinds of roofing profiles, they are all put through a roller, which I'll show you in the next slide. But these ones can be folded as well, and are used in steel stud frames. So these are very lightweight bits of steel that are spot welded together or riveted together to form walls. These are very cheap to produce, and for their weight, they can be very strong as well, and very commonly used. So next time you are in the Bunnings or the Office Works, or even the supermarket, well, actually mostly Bunnings and Office Works, if you look up and look at, you will first of all see probably some sort of hot rolled section as a post and as the beams. And on top of that, the things that are connected to the roof, the purlins, are generally cold form sections. All right, so what you guys should try and do is to identify the bits of steel that you can see around you, and see if you can figure out whether it's a cold form or hot rolled section. So with the cold form sections, basically you've got the thin bits of steel which is all coiled up like this. It can be coiled up and pre-painted, as you can see here on the right. And through a series of rollers, you can then get this roofing profiles that are coming out. So these roller things are actually can actually just sit on the back of a truck. So what you can have in very big projects, such as the new Melbourne Convention Centre by NH Architects and the Victorian Government, they actually bring the coils of colour-bond steel out to the site. They have the roller on the back of a truck, and they basically roll it out and basically lift it straight up onto the roof. So it's rolled up onto the roof, because of course if you have to ship it out there, you know, like articulated trucks can take something up to about 11 meters, but the roof on the Melbourne Convention Centre in parts is about 60 or 70 meters long, and it's one piece of steel. Okay, so there's we are figuring out different ways to use this kind of technology by bringing it to the site, because of course these things will happily sit on the back of a truck and not even need to be a very big truck. In these two pictures here, you can see on the left a house that is being framed up with cold form sections, the thin ones, but in-house architecture and construction, we also use hot rolled sections. So in this picture here, you can see the use of square hollow sections, and you can see the back of a channel here being used as a lintel, which is the thing that holds up the roof. Right? So the use of hot rolled and cold form sections is not exclusive to any one type of building or one type of application. Quite often they're used together. Now, other uses for steel is as a cladding. So not only on buildings like the Melbourne Convention Centre, but also a lot of houses. Now, these are two award-winning houses in Canberra where they've used a colour bond profile. And this house here, which uses the long line profile, is by Ben Walker Architects, who's actually teaching at our university in the third year design studio. More solid pieces of steel are also used in architecture. This kind of steel, what we see here, is called Core 10. It's actually a steel that architects use because they like the rusty look to the building. Okay, it has a characteristic where it will rust to a certain level, and then the rusting will dramatically slow down. In due course, the rust, of course, will eat through it, but if you can get 20 or 30 years out of it, then the steel has done its job. Now, rust is one of the main, rust is the way that steel degrades and iron degrades, right? And no steel or no steel or iron product is immune from rust. Even stainless steel will rust in the right conditions, right? So all iron and steel products will rust in due course. The other name for rusting is oxidation. So it's a chemical process which where the exposure of steel to the air actually creates this process. Now rust the characteristics of rust is that it is flaky and its volume is something like 20 times the volume of steel. So when steel converts to rust, it tends to poof up and fluff up, right? Which is very annoying. So what you want to do if you don't want a rusty building is really that you need to have to coat or protect your steel with something. And this is true of all metals. In some cases, as we will see, the oxidation of some metals actually add to the surface strength of the metals. The only metal I can say that doesn't oxidize in that way is actually titanium. So titanium is something that you can actually leave in salt water indefinitely and it will have no detrimental effects to the titanium itself, which is why divers' knives are often made of titanium. Now, we'll move on to other metals just quickly. So they're not generally used for contemporary primary structure because there is just so much iron ore around and so much steel around, and because of the cost of turning other metals into elements of the same strength. So either it's going to be cost too much, or it's going to have to be really big in order to get the same strength as steel. So if you look at pipes, for example, or tubes, an aluminium tube can be just as strong as a steel tube, but its cross-sectional area will need to be quite a lot larger than that of steel, right? So other metals are generally used also because of their properties in terms of the way that they can be manufactured made into different things, and also because of their resistance to water degradation. So I would say that aluminium, copper, brass, zinc, and zinc and lead rather are all materials that that have better performance when exposed to the environment than steel, right? And because of that, they're often used as cladding. Let's start with aluminium. So aluminium nowadays is most commonly used for door and window frames, where they are basically extruded. So what happens is that they come in big bars, long bars, and because aluminium is relatively soft, you can actually push it through a die, which means something in the shape of a profile, such as this profile you see here. And what will emerge out of the die is basically this shape here. So this one here would have been basically a rectangular block that's like that. That's basically been pushed through a die, and it comes out as that shape. Okay, so you can't actually do that. You can't actually do that with steel unless it is heated up. With aluminium, you can do it at room temperature. Okay, which means that there's one step less to get this done for aluminium, which is why it's used so regularly in this. You can make it, if you make it into certain shapes, oopsies, it can be actually quite strong, and us inventive humans have figured out all different ways of extruding it so that it can clip together, be screwed together, and so on and so forth. So this is really one of the more common forms of making door and window frames, especially in commercial and office type and high-rise type applications. Quite common also in residential applications. In fact, becoming more so as timber is getting more expensive and harder to find in large sizes. Aluminium is also quite good as a sheet, so it can be used just as a basic sheet, as you can see here, or as it can be made into sandwich panels. The ones on the top have been sandwiched with sheets of plastic about 6 mil thick to become a form where it's much stiffer than this one, which is just the aluminium by itself without being sandwiched or anything else. Anodizing is a process by which aluminium gets its strength. Its surface gets its strength and its weatherproofing. And naturally anodized aluminium is essentially the natural oxidation of the pure aluminium, and is that kind of matte silver look that you find on a lot of aluminium, which is very hard and very impervious, resistant to scratching and so on and so forth. So really the opposite of rust, right? So aluminium rust actually acts to protect the raw aluminium, unlike steel or iron rust. Yeah, so us clever humans have figured out ways to control this process of oxidation, to get colors into it, and sometimes even textures into it as well. Now, moving right along, the next metal I'd like to talk about is brass. Now, brass is also an alloy. I can't remember what the alloy of what goes to make brass, but essentially brass is this kind of goldy greeny color. Its particular property is that it does not degrade when it comes into contact with water, which is why brass is often used for plumbing related fittings, like taps and connectors and so on and so forth. In fact, all of the chrome taps that we see in our bathrooms are actually made of brass and then chrome plated. So if you ever go and see something that that says that has the abbreviation CPB when in reference to a tap, it means chrome-plated brass. Okay, so brass is basically the stuff that's doing all the work, being exposed to the water, meant to hold together without rusting. It doesn't degrade in water, and the chrome is really what we like to look at. Copper is another metal. Copper has been used for many years, started off being used as a cladding, because when copper oxidizes, it goes from this shiny material here to being this green material here. And once you get that green coating on it, that green coating is also very strong and thus will not degrade when it's exposed to the weather, to the climate. Yeah, copper's also has historically been used as pipes, water supply pipes, as well as waste pipes. Again, because it's impervious to, it doesn't degrade in water. But more recently, we're starting to use reinforced plastic pipes rather than copper because of the cost of copper. Any questions? No questions. Okay, very good. So moving right along. The next thing I want to talk about is zinc. Zinc is another thing that's used as mostly as a cladding nowadays because it will degrade in a certain way, which is where it's going to maintain the way that it looks, and its oxidation is actually very slow and creates a nice patina to the building. So you can see here it's got that kind of matte finish to it, whereas when it's new it's got this slightly shiny finish to it as well. Yep, so this was done quite commonly. It's still used, but nowadays it's quite expensive and only used in special occasions or special buildings. And finally, we have lead. So lead is a poisonous metal, but like the other ones that we've looked at, it doesn't degrade when exposed to water or to the environment. Lead has been used a lot in roofing in the past, but mainly because of its softness and its ability to be pressed down and molded into other things. Lead is quite often used as flashings, and flashings are the connections between two different planes. So what you can see here is a slate roof and a brick wall, and the lead flashing is actually folded in between the bricks and then folded around the lead roof in order to waterproof this connection. Again, here you can see this curved lead roof here, which it's also folded into the brick and pushes the water away from the wall. Here again, another roof and a brick wall. Any questions with this? Or comments? Yes. Look, with all of these materials, they are all still used, primarily because they are very long-lasting materials and they exist on buildings. So especially if you deal with older buildings with lead flashings, really that is, you will still have to use it. Yeah, and it is a really good material, especially when you're trying to match up two different lumpy materials. It actually forms very well to it. So of course you don't want to be eating it, but it does, because it's so soft, you do need to have a solid substrate underneath it so you don't just step through it. But yes, of course, you know, the architecture and construction industry is one where we don't only deal with new buildings, we quite often deal with older buildings, so it's important for us to be able to identify all of these things when we come across it. And of course, one other thing I will mention is that there is a process called galvanic corrosion. Okay, there is a process called galvanic corrosion, which means that when two different metals are connected by a stream of water, that will create a bit of an electrical circuit, which will then result in the degradation of one metal over the other. Okay, so it is important. I mean, it's not really relevant for this lecture, but this is why certain types of metals are used in a certain sequence, and certain types of metals will be used downstream from other metals in order to prevent this kind of galvanic corrosion. Again, it's not something that's common nowadays because of modern materials, but you will still come across it every now and again when you're renovating older houses, which many of you will be doing. All right, are there any other questions? Yes? No, it's not. No, it's not. And I think that only happens in certain circumstances. Like if you open up most taps, you don't see the green stuff inside it. Yeah, it's only if you've got standing water. You know, often you see it around the treads of the connectors, but it's not hazardous. No. Yeah. Any other questions or observations? Very good. Then it's a nice short lecture for you, and we can all go and have a coffee. Thank you all very much.